All right, in this video, we'll look at 2 examples of how to run a hypothesis test. This first example is going to show a breakdown of the steps that we talked about before. Then I'll go through the second example. If they weren't outlined for us, how would we go through the problem? So we have a current antacid provides relief for 70% of the people who use it. And then a pharmaceutical company has a new drug and they want to test to see if it is more effective. So they run a study with 100 randomly selected patients, 75 experience relief. Is this drug better? So some pieces that come from the wording here. They talk about what's happening with a current antacid. So that's kind of describing what we expect in our population. We have the wording that they want to test whether it is more effective, which is describing our alternative hypothesis. And then we have this information from a sample. And that is typically everything you'll be given with this questions about hypothesis tests. They'll give you something they assume is true. They'll tell you what they want to test or find evidence for, and then they'll talk about their sample data. So for writing our hypotheses, we want to ignore the sample data. So what they're telling us is that we would assume that if we made an antacid, that it would provide 70% relief. So we would assume a 0.7 there. Then what we want to test is whether it is more effective. So we want to show that it's actually larger than 70%. So there's our null and alternative hypotheses. Second part is checking our conditions. So independence. We would have independence here. If one person finds relief from an antacid, that's not going to change how another person's affected by an antacid. So I'll be independent. Randomization. We would want to be taking a random sample, which they do say in the wording it is a random sample. So we definitely know we have that. And just like before, if those aren't clearly stated, you can go ahead and assume that they are random. Then we want to check our success-failure condition. Would we have large enough samples if we applied this hypothesized proportion to our sample size? So we're going to use our sample size of 100, but we want to see how would that behave with our proportion from our hypothesis, which is 0.7. And how would it behave with 1 minus that value, which is a 0.3? So we'd have a 70 versus 30, and both of those are more than or equal to 10. So we're all good there. So we pass our conditions. Then it's in this step that I like to draw myself a little picture just to help myself out when we go to Geogebra. What I would notice is that we're using the more than symbol. So we're trying to show for a large value for p, which is going to make this a right-tailed test. Which means when we get into Geogebra later on, and we find our test statistic wherever it's landing on this right-hand side, p-value is going to be this area to the right. And I just like to draw myself that little picture to remind me how to find p-value later on. What we could also do in this step is kind of write out our rejection rule. Like we are going to reject that null hypothesis if our p-value is smaller than, and then we just need our significance level, which if you notice in the wording here, they didn't state a significance level at all. So that's where we just assume it's 5%. So we assume it's 0.05. So that gives us our cutoff for where p-value small versus large. All right, now calculating p-value. We want to find our z-score. To find our z-score, we need to look at the sample proportion that we found here. So that's 75 out of 100, which is a 0.75. So when we go to make our z-score, we're going to take 0.75 minus our hypothesized proportion over, and then that standard deviation formula, just remember to always use the proportion from the hypothesis there. Again, this 0.75 from our sample is just showing up in the numerator there, and that's the only spot. All right, if we plug that into a calculator, we should get out a 1.0911. And then this is where we go to Geogebra. What we want to do is in Geogebra, using that standard normal curve, we want to go to that curve and have this cutoff of 1.0911, and we want to find this area to the right. So this p-value is going to come from this probability of being larger than or equal to 1.0911. So in Geogebra, we want to find area to the right, and we want this cutoff for the area to be 1.0911, which is going to give us an area of 0.1376. And that is our p-value, the area to the right of the test statistic. So now for our conclusion, what we want to do is take our p-value, take our significance level, and figure out which one's larger. And it's going to be our p-value is large. Again, you can compare those as percentages. So like 13.76% is larger than 5%. So p-value is not small, which means we failed to reject the null hypothesis, which means there isn't evidence for the alternative. In terms of writing conclusions, what you'll see in other materials is that they just write down, like, reject the null, fail to reject the null. But I find it really helps me to write down all three of these pieces, so I know how it all comes together when I make the wording for the conclusion. But talking about what happens with the null hypothesis is kind of the main conclusion there. And then making our sentence, that's where we want to talk about our alternative hypothesis. So with a p-value of 0.1376, there isn't evidence that, and what we were trying to do is they ran a sample, we saw the 75%, but basically this new drug is not significantly better. Even though, and this is kind of tricky because that 75%, I mean, just comparing that 70% with 75%, obviously this new drug is better. It's a higher percentage finding relief. However, if we took random samples of 100 people with this idea of 70% coming through, seeing a group with 75% is a likely outcome. So that's where this isn't significantly higher. And even looking at the picture in Geogebra, this is showing a high probability of occurring. There's a large percentage chance, if you think of this as the sampling distribution from if I talk to 100 people using this new drug and how many feel relief, in the middle would be 70%, and then a little above and a little below, but basically seeing that sample result, which is the cutoff for this line here, that's where our 75% is landing, and it's close to where we expect to land. So with that, it's not a significant difference coming through. So basically there isn't evidence that this new drug is significantly better. So there isn't evidence that the new drug is significantly better. Now, with Geogebra, there is a way to double check our answers. If you go into Geogebra, and sorry my screen's cutting off a little bit, but at the top there are these two tabs. It's currently in Distribution tab, and it's in this upper left-hand corner. What you can do is switch to Statistics tab. So if you see in this upper left-hand corner here, I switched to Statistics. I'm really sorry this is cut off, but we're so far in the video, I'm not going to change it. If you go to this drop-down menu, there's all these different tests here, and down here's estimates, which link to confidence intervals. So working with confidence intervals, you could play around with this Z estimate of a proportion That would relate to confidence interval for a proportion. And what we're doing is z-test of a proportion. So z, because of our z-score, we're doing a hypothesis test, and we're just looking for a single proportion. All of these other scenarios come up in Math 244 when you do the second course of statistics. So if you go to z-test for a proportion, it comes up with all these values. So like the null hypothesis, you just type in what's in the null hypothesis. So like for us, it's a 0.7. Then you put in the symbol that matches. So like we're using the more than symbol. So we'd have that. And then for your sample, you just type in basically the fraction that makes your sample statistic. So like in the numerator, we had 75 out of 100. And what this will show you down here is z, it'll show you your test statistic, which is z, the 1.0911, and then p is our p-value of 0.1376. Now, I'm showing you this to show you how to check your solutions, but you should be able to show your work in terms of how to calculate the z-score and finding the values. It's hard to show work for finding values in Geogebra, but you should be able to do that by hand, but use this as a resource to double check solutions. So that's under the statistics tab. But if we go back to the distribution tab, that'll bring us back to our bell-shaped curve. All right, second example here. We have a company develops what it hopes will be better instructions for its customers to set up their smartphones. The goal is to have 96% of customers succeed. The company tested the new system on 400 people, of whom 376 were successful. Is this strong evidence that the new system fails to meet the company goal? All right, what we have here, well, over here's our sample data. So in terms of setting up our null and alternative hypothesis, we kind of want to ignore that. What we're going to do is assume that they're meeting this 96%. So first step, we assume they're 96% successful. What we want to show is that they're failing to meet this value, which would mean this proportion is less than 0.96. So we want to show that that's lower. So that's our first step. Then we should check our conditions. So make sure we have independence, which how people read instructions and how successful they are in setting it up. Those are independent. They didn't say it's a random sample, but we'll assume we're good there. And then success failure. We would take our sample size of 400, multiply that with the 0.96, take the sample size of 400, and multiply that with 1 minus of a 0.04. And so for these values, we would be getting out a 384 and a 16, which both of those values are more than or equal to 10, so we're good to move forward there. Then I'm just going to make that little note to myself that this is a left tail test. So once we get this distribution out, wherever our test statistic lands, which it should be on the left-hand side there, we're going to find this area to the left to find p-value. And then we're going to reject that null hypothesis if that p-value is smaller than our significance level, which doesn't state a significance level in the wording of the problem, so we'll just assume that's a 0.05. All right, so there's our setup there. Well, then it's calculation time. So we're going to find, we need our sample statistic, p hat, which is the 376 out of 400. So from the sample, we saw a proportion of 0.94. So we can tell that that's less than what we expected, but what we want to know is it significantly less than what we expect to happen. So for our z-score, we'll take our sample statistic of 0.94 minus what we expected to come out over our square root, and then use those values from the null hypothesis, 1 minus that, over our sample size of 400. And that should give us a z-score of negative 2.0412. So using that value, we want to go into Geogebra, and using our standard normal curve, we want to look at if we have this cutoff, at negative 2.0412, what is the area to the left? And that will give us our p-value. So in GeoGebra, we'd go area to the left, and then just edit our value to the negative 2.0412. Hit enter, and that's a 0.0206. So, with that p-value, compare it to our significance level, so 0.0206, compare that to a 0.05, and which is smaller, and it's going to be our p-value is small, which means we reject that null hypothesis, which means we have evidence for the alternative. This is the scenario we like. We found the evidence that we went searching for. So, with a p-value of 0.0206, there is evidence for, and we just want to look at the wording of our question. What did we want to find evidence for? And it's that the new system fails to meet the company goal. That's what we found. There is evidence that the new system fails to meet this the company goal. All right, and that's how we run our hypothesis test. We just need to get through those 4 steps to get to the conclusion.